Okay, hey folks, so continuing along, so now I want to describe in more detail our activation controlled reactions. We'll do this primarily for the gas phase because it does get really complicated in the solution phase. And we'll rely on transition state theory to help us with this description. So now we have the same mechanism that we described before, where we have an A plus a B, and they may diffuse to each other. They could diffuse to each other in the gas phase or in the solution phase. They form this unstable intermediate, or really I shouldn't even say unstable intermediate, right? They form a transition state. That transition state can fall apart back to reactants or can go forward to products. And this was the same expression we derived last time using a steady state approximation, only last time I used, just so we are clear, KD prime, and KA. To be consistent with kinetics literature, I changed that to K forward, K reverse, and K double dagger. So if you recall, if K double dagger is limiting, or in other words, if K double dagger is much, much less than K reverse, as in the case with an activation controlled reaction, right? So diffusion is not limiting our reaction here, rather activation is limiting our reaction. Then recall this expression becomes the following: dP by dt equals, so we can ignore K double dagger. K forward over K reverse becomes our equilibrium constant, and now I'm going to write this as small k double dagger times big K double dagger, all times A, all times B. And now the game to play here is to really start thinking about what this equilibrium constant is, not only in terms of its activities or concentrations, but also in terms of its statistical mechanics, so in terms of its partition functions. So as a reminder, we could write this K double dagger with the following. We could call it the activity of our transition state all over the activity of A times the activity of B. And what we really want to get into now is, if we think about these activities in terms of their partition functions, then we can learn some things about our reactions. So let's switch the page here, and I'm going to change this up just a little bit. Instead of a simple reaction, A plus B goes to C, and then C goes to products, I've put a bond in here so we can see the nature that our chemical bonds will play. So in other words, an A molecule goes to react with BC. That forms the transition state ABC, okay? So ABC. So our electrons are starting to enter into stable orbits, but they haven't quite formed the new product yet. And when it forms the new product, right, we're breaking the BC bond and forming an AB bond. So we're actually doing chemistry here. So if we zoom way in to the top of this thing, right? So zoom in. What we would actually find is there is somewhat of a stable minima at the top of that activation energy. And that minima we can describe using our harmonic oscillator model, which we will describe in great detail when we get into 362. But effectively what we have here is a model that describes two masses on a spring oscillating, which gives us this parabolic energy well, and also allows us to see our state-to-state dynamics, right? So our ground state is the ground vibrational state. If we pump energy in, right, we can get that up to the excited state. So down here at the ground state, the bond is much more compressed, right? As it goes up, it expands as it vibrates. So our transition state can be stabilized depending on the nature of this potential energy well. And now, if we dive deep into our partition functions, we can write the equilibrium constant as the following. So instead of it being activities of products over reactants. It's the partition function of the product over the reactant, as well as this energy contribution related to the Boltzmann distribution. Okay, so if you recall Q, these partition functions, right, they went something like this: 1 over 1 minus E to the negative delta E over KBT. Okay. So, and it's also important to note here that that energy, that is going to be equal to H nu, so the vibrational energy of our molecules. So again, those kind of vibrations really make a difference in how we think about this whole situation. Okay, so that's all that I wanted to set up for now with this. In the coming videos, we're going to describe what people typically do with this. So how people look at the partition functions as well as the vibrational energies to assess the dynamics of these types of mechanisms. Okay, so more on that to come in the next video.